This demo represents the development of 3DAVis, a system that renders astronomical data into a three-dimensional visualization using a client-server hybrid rendering approach. Its goal of serving as a proof of concept for future three-dimensional astronomical data visualization tools. Astronomy is a visual science that relies heavily on visualization. So visualizing datasets that are gathered by modern telescopes is necessary for astronomers. Without current visualization tools, astronomers will have very hard time observing datasets that are gathered by these telescopes. The new generation of radio astronomy telescopes, due to increased size of data being captured by them, requires improved software designs and visualization techniques. This is required to maintain or enhance interactive performance and user experience when dealing with large datasets. Our project uses client-server approach and also hybrid rendering design. We will talk about these in detail later in presentation. Before we start more in detail with our demo, it is good to have some background knowledge. Around 1 billion astronomical data that is gathered by astronomical instruments worldwide are stored in FITS format. The FITS format is a very generic format and used to represent large amount of different data types. There are numerous advantages of FITS file format in astronomy. Another file format will be HDF5 format. HDF5 datasets with the continuous layer strategy nearly conserves access time to any element in the array, and zero overhead for locating elements in a dataset is assured. HDF5 file format can stream sections of files across multiple spindles and has a very high read-write speeds. HDF5 format also offers storing data in chunk datasets. Chunk datasets are split into multiple chunks that are all stored separately in the file. Chunks can be then read and written individually, improving performance when operating on a subset of the dataset. Volume rendering is used in scientific visualization to create 2D projections from a 3D dataset. We are using direct volume rendering, which is type of volume rendering where only simple algorithms are used and no approximations are applied to the data. From direct volume rendering, we will be using volume raycasting approach because of its high quality results. VTK, which stands for Visualization Toolkit, it was created for the purpose of displaying manipulating scientific data. VTK supports volume rendering. There are different versions of VTK such as C++ library and the JavaScript library, which makes it easier to use in our server client design. ZFP is an open source C++ compression library format for representing multidimensional floating point and integer arrays. ZFP also supports parallel compression of whole arrays. ZFP is mostly known for its lossy but optimally constructed compression, which can reduce data by a factor up to 100 times.
The goal of our research project was to construct a proof-of-concept system that implements a strategy for allowing any average computer to produce visualizations of very large data cubes in a lag-free manner. We formulated a series of research questions which we intend to answering through the completion of this project. These questions mainly relate to the usability of the new system, the libraries used for compression and rendering, as well as the scalability of using large datasets. The strategy for addressing out the research problem is to implement a system using a server-client model. It would combine server and client-side rendering, but the majority of the computational overhead would be offloaded onto the remote server. The data cubes would be stored onto the remote server, and users can access them through a client computer connected to the internet. The server can send volume and image data respectively to the client on request. The volume data comprises of three-dimensional data cubes, which could be a portion of a larger data cube. These smaller cubes have been downsampled by a certain factor using MIC mapping. The image data is a high-resolution rendering of the data cube, and these images are produced by the server, which could have enough computational resources to produce the visualization. When there is no interaction on the client side, it displays the high-resolution rendering, and when there is interaction, the client switches to rendering the volume data it receives. This makes interaction with the data almost instantaneous, and the user does not have to wait for the server to produce more frames and stream them to the client.
Disk reading is a slow process in computers. HDF5 file format provides higher read speeds than FITS format For us to be able to use HT5 format, we need a converter that converts from FITS to HT5 format, since a huge portion of astronomical data is stored in FITS format. While converting astronomical data, it gets chunked in small cubelets with dimensions of maximum 64, 64, 64, which makes it 1 megabyte in size, which supposedly results best reading speeds from SSD when data is read in these small cubelets. After implementation of this design, testing has been done on this, and the server achieved reading speed equal to SSD's maximum reading speed potential. After server checks cache, and if needed cubelets are not in the memory, it reads from the disk. With the threshold of 1 gigabyte, there are gonna be more than 1000 cubelets, and these cubelets needs to be constructed to one big cube. Reconstruction algorithm has been implemented for this purpose. This reconstructed 1 gigabyte big cube is rendered on GPU using VTK library. Then this volume is set to camera and color parameters that are received from the client. Then volume's front view is encoded to high resolution image in JPEG format. Then this image is sent to client.
WebSocket is a computer communication protocol which provides full duplex communication channels over a single TCP connection. Therefore, as in the diagram on the right, it provides a bidirectional message connection where the server and the client can communicate at any given time. In our case, the client will make requests for specific pieces of information which will allow rendering and interaction on the front end. The server will reply to those requests by pre-processing data cubes and sending through the relevant compressed volume data or high-resolution image. There are several requests which are required for the proper running of the system. Once connection between the server and client is established, the server firstly sends a list of files available for render. The client then displays those files, and the user can select a file of interest from a drop-down list. After file selection, the server is made aware of this activity and proceeds to sending the big file dimension JSON, which basically consists of the sizes of the smallest files in the X, Y, and the Z dimension. This is essential for the client to determine which specific task to request as the user interacts with the data. Then, the server and the client gets in an interaction and no interaction loop, where the volume data and high-resolution image are transferred respectively as per the user's activity. ZFP is a C++ open source library and is directly implemented on the backend as a compression clause library. It compresses volume data into a vector of binary characters, which is then converted to base64 string during transfer to the client. On the client side, things are quite more complex, as the decompression clause needs to be comprehensible to the JavaScript's interface. Therefore, Enscripten is used as a front-end tool compiler to convert the C++ decompress method into JavaScript and WebAssembly. Some TypeScript, that is the pre.ts and post.ts, are required for the smooth running of the wrapper. For this project, we were able to create the WebAssembly file, but the Vue framework was unable to import it from its Node modules as compared to the React platform of Kota. Therefore, we included this as a limitation of the project.
Hi everyone, I'm Michaela, and I was in charge of creating the client portion of the system. The client system is a website built using the Vue.js framework. It allows the user to access the data and functionality of the server. It uses a VTK.js to render the volume data it receives from the server and facilitates interaction with the data. VTK.js is a JavaScript library that allows for the rendering of scientific data. It also reconstructs the tiles it receives from a single cube to be rendered by VTK.js. The reconstruction algorithm is currently not optimized for the client system and needs some reworking, but only affects the system if it has to reconstruct multiple cubes, say larger than 2. However, we limit the number of cubes the client receives to 2, so that's not an issue. This caps the size of the data that would be received and the amount of time the client would need to process the data, excluding the time it takes for it to render it. The client system must also determine which tiles to request from the server if the user would like to look at a certain section at a higher resolution. Once the cube is cropped, the client system determines which level the required tiles are on and which tile IDs to request. During the completion of the system, there were certain limitations that affected the quality of the final deliverable. Since the scope of the project was quite large, we knew time would be our biggest limitation. We found that working in different locations from our team members did affect the speed of our system development. Our supervisors did warn us about wasting time selecting packages to use, so we did our best to decide on which packages and libraries to use beforehand. However, we still got caught up in the learning curve for some packages. Like for me personally, I had to learn how to use VTK.js as well as a little bit of the original VTK library. The system we have implemented shows promise and could definitely benefit from further development, as well as addressing areas that would require further development. I know of something that I feel I could have developed further was the tiling algorithm that I implement on the client system. It works for certain base cases, but it does not address many edge cases and produces an error when it encounters those cases. Future development of the system would include adding the compression package ZFP to compress the image and volume data that the server sends to the client. If the server was hosted remotely, then the compression would assist in reducing the time to transfer the data over network by decreasing the amount of data that would need to be transferred. We would also host the server remotely and deploy the client JavaScript application so that the proof of concept can be fully realized. For this demonstration, the server and the client applications are running on the same local machine. First, when the client application is loaded in the browser, the user must select the file they wish to view. The server sends the initial volume and image data to the client. With the volume data, the user can interact with it by rotating, zooming, and manipulating the crop area and the color of the transfer function, which determines the color and opacity each voxel is assigned during rendering. Once the user has cropped the data, the client then requests a higher resolution data cube of the cropped area. As you can see, after the crop, there is more detail visible than previously. Cropping the data can be performed multiple times and can show a smaller part of the full dataset at a higher resolution.